Okay, let's study the common emitter amplifier that is drawn on figure 14 of lab 13, or we're calling it lab 13, 14 because you have extra time to do it. So I redrew the schematic diagram over here, and then we can talk a little bit about how the common emitter amplifier works. So the common emitter amplifier that you see in this figure is sort of an embellished version. So let's start out thinking about the common emitter amplifier in its simplest form. So we will take an NPN transistor, and we're kind of accustomed to the input coming at the base. So here's our base and our collector and our emitter for an NPN bipolar junction transistor. And let's suppose that we have an input signal at the base. So here is our time axis, and here is, I'll draw a bunch of voltages on the same axis. So let's start out with the base, and let's initially say that the base voltage is just flat here at, let's call this VB. And then I guess we'll add a little wiggle to this, and we'll see what happens. Okay, so let's start out here where the base is at some constant voltage. So then here is our B base. And notice I lifted this up above 0 because we want to make the transistor be active. So normally we have this biasing network to do that for us, or there are other tricks we could use. But let's just say we make life simple for ourselves by introducing a DC offset. So somehow we want to make sure that this base emitter diode-like junction is active. We want the transistor to be active. So if we lift this up a little bit above ground, then we can, actually we could just ground the emitter, and then that would turn on the transistor. But that makes it a little bit hard for us to control the current that flows at the emitter. So in order to make it easy for us to control the current that flows at the emitter, we will put an emitter resistor here, which is what we are accustomed to doing in the emitter follower also. So then here I'm going to call this the emitter voltage. And you know that for an active NPN transistor, you have VBE is a diode drop. So it's like, let's say it's about 6 or 7/10 of a volt. I guess we've been saying 7/10 more often than 6/10. I mean, exactly what value it is sort of depends on how big the collector current is. Let's say it's 7/10 of a volt. Okay. So then this is, the base minus our diode drop. Okay. And actually, let's just give this some nominal value. Suppose this is like 2.7 volts. Okay. Then that's 2.7 volts. Then, yeah, if you say that's 2.7 volts, for example, then this would be, let's say, 2.0 volts. I'm not following anything we set up over here. I'm just sort of making this up so we can kind of see how the common emitter amplifier works. And so then we start at the base, and again, we start out assuming, you assume that I base is negligible. And actually, I guess that assumption doesn't matter too much here because we don't have a voltage divider network here, but normally we have this biasing network, and then what I base is will affect what V base is. Here, let me get down a little bit out of the way. So then we know what the base emitter, we know what VBE is. It's a diode drop. So now we know what IE is. So then you say, okay, now you have IE is now, of course, it depends what this voltage down here is. In all of the emitter follower and common emitter amplifier circuits we've drawn to date, this voltage down here has been ground. Sometimes you make this a negative voltage called VEE. Like if this is VCC up here, this is VEE down here. So I'll just write it assuming that this is ground, but you want to use Ohm's law in a way that correctly uses this voltage down here. So this would be the emitter voltage divided by this emitter resistance. And then we could say, well, what do we think this, I mean, you know, if we make this, for example, 1 kilo ohm, then if this is 2 volts, in this case, we have 2 milliamps. Okay, so yeah, typically like 1 or 2 milliamps is a common value for the so-called quiescent. That's the current through the parts of the transistor when you're only looking at the DC conditions. You're not yet looking at the AC kind of perturbation on top of those conditions. So, okay, I'm kind of making this up as I go, but I think this way you can kind of see what I'm thinking. So now that lets us determine this emitter current. So far it's the same way we analyzed the emitter follower. And then remember that once we allowed for an AC signal, then as VB goes up and down, VE goes up and down the same amount because this diode drop stays quite constant. It only changes very, very slowly as a function of, let's say, the base current or the collector current. So, you know, if you have VB go up by delta, then VE goes up by that same delta, and then IE goes up by that same delta divided by RE. Okay, so now we can actually exploit the fact that this IE goes up and down in proportion to the change in VB, right? So here, let's just write that out again. So you know that you know, you apply some delta VB at the base, then diode drop. That means that delta VE is the same as delta VB, or pretty darn close to the same. And then that tells you that delta IE is delta VE divided by RE. So this delta statement is true no matter what fixed voltage this is, although the quiescent current will depend on this voltage difference divided by this resistance. And then you know, so then you know that the base current is the collector current divided by beta, so that's much less than IC. And so then we know that the collector current is about the same as the emitter current, right? Because we have the emitter current is the collector current plus the base current, since the direction that we use for the base current is into the transistor, and the direction that we use for the collector current is into the transistor, but the direction that we use for the emitter current is out of the transistor. So because this base current is tiny, as long as the transistor is in active mode, as long as the transistor is not saturated, then we say, okay, the collector current is about the same as the emitter current. So then that says that delta IC is approximately the same as delta IE, which is delta VE over RE, which of course was the same thing as delta VB over RE. So far, so good. And then, now of course this all depended on, remember in the emitter follower, we just connected the collector directly up to plus 9 volts or whatever our power supply was, up to VCC. So the little trick that we use in the common emitter amplifier is, here, let me just make a little space here. We stick a resistor up there. So by putting a resistor up there with a fixed voltage above it, as the collector current increases, the collector voltage decreases in proportion. So here is the collector resistor, and then we call this VCC, which in our Electronics Explorer board has tended to be 9 volts. Okay, and then the output of this circuit is over here. Okay, so this collector voltage is our output. And again, remember, our goal is to make a circuit that kind of behaves in an analogous way to the inverting amplifier that we're accustomed to from op-amp world. And you remember that in op-amp world, we have our op-amp, here's our output, here is our input, and we had 2 resistors, and we said V out is minus R2 over R1 V in. That was for our op-amp inverting amplifier, so we want a transistor circuit that's somewhat analogous to that. Okay, so we're going to see that V out is basically minus RC over RE times V in, at least the AC portion of it. Right, so let's go back up here, and we'll say we know, we already have that the change in the collector current is the same as the change in the emitter current when we wiggle the base, which gives us this expression, the change in the base voltage divided by RE. So now notice that the voltage at the collector is just the fixed voltage up above the collector minus the collector current times this collector resistance. Okay, and again, this was IC. And this is just a fixed value. So if you have take a derivative, then we have the change in V collector is just minus RC times the change in the collector current. And then we can just plug in a value from here. So then this change in collector voltage is minus RC, and then here, right, here's delta IC. Delta IC is just delta V base divided by the emitter resistor. So there you go. So we have basically the change in the collector voltage with respect to the change in the base voltage is just minus RC over RE. So this ratio of 2 resistances gives us the gain for an AC signal, for the time varying portion of our input signal. So if the base voltage goes up by 1 volt, then the collector voltage will go down by, well, let's say maybe it goes down by 10 volts if this ratio is 10. Okay, so that's kind of the basic idea behind the common emitter amplifier. So once again, we always start by asking what's happening at the base, and we arrange things so that the transistor is active. And then we start out setting things up the same way we did for the emitter follower. So we have this resistor called the emitter resistor between the emitter and some fixed voltage. So in our case, that fixed voltage is ground. And then we say, okay, when there's nothing happening, we know what the we know that the emitter is just a diode drop below the base, and then we know the emitter current is just this emitter voltage divided by this emitter resistance. And then because the transistor is active, not saturated, then the same current that flows out the emitter flows into the collector to like maybe like on the order of a 1% correction. So by changing the base, we're changing the emitter current, which changes the collector current. And then if we put a resistor here, so we have a fixed voltage that we call VCC, and there's a resistor down to the collector, and we take the output at the collector, then you know that when this current goes up the same amount, and then because this is a fixed voltage, this is a resistance, so this voltage goes down in proportion. And then we can make this ratio of two resistances such that we get the voltage gain that we want. So again, the change in the collector voltage with respect to the change in the base voltage is just minus the ratio of these two resistances. Okay, then we can talk about the complications that we had to add. So first of all, it's inconvenient to have to add a DC offset to your input signal because you probably want to be able to amplify a signal that varies with respect to ground rather than that varies with respect to some fixed offset of a couple of volts. So to arrange for that to happen, we put this blocking capacitor, C1, in place. So then it looks like a short circuit to AC signals, and it looks like an open circuit to DC signals. So you make this capacitor big enough that, you know, it's together with some resistors down here, it's going to look like an RC high-pass filter. So you just want to make sure that the F3 dB of that high-pass filter is low enough that any signal that you're interested in gets through, unimpeded. So I think in our case, actually I don't remember the number now, but you want to make sure that so we have F3. Remember we had F3 dB is 1 over 2 pi RC for an RC filter. And so you want to arrange this capacitor value together with the parallel combination of these resistor values so that any frequency you're interested in amplifying is well above that cutoff. And then, so the purpose of this capacitor was to allow the DC phenomena here to be separate from the DC phenomena here, but the AC signal passes through. And then you say, okay, now we have to arrange R1 and R2 so that the base is in some comfortable place. So let's erase a little bit and talk about how we decide where to put the base. So we have a little bit of a trade-off here. I usually like to show you the simplest version of a circuit and then add complications gradually, one by one, so that your mind has time to absorb the uncomplicated version, and then you can kind of add on one complication at a time. On the other hand, if you're building things at home without our help to look over your shoulder, then we kind of have to limit the number of distinct things that you build. So in this case, we're sort of going right into a more complicated version of the circuit. So, okay, so we talked about the fact that one complication is we want to separate the AC from the DC signal. So that's what this capacitor is for. And then we need to bias the base so that the base voltage starts out high enough that we can have, our diode drop VBE, and we can also have the signal at the base have some room to wiggle up and down. And then, so that's what this R1, R2 combination is doing. And then one more complication that we're adding is, you might remember, at some point we used an op-amp circuit to amplify a microphone signal. And in this case, it was a non-inverting configuration of the op-amp. And let's see, what did we do? We put one resistor here, and then we put another resistor here, and then we put a capacitor down here. And remember that in the case, this was the non-inverting op-amp circuit. So you've seen me derive this several times. So I'll just write down the answer. It was V out is V in times, okay, so let me put these things together and call them Z1, okay? So if this were just a resistor, this would be V out is V in times 1 plus R2 over R1. But this R1 is not just a resistor, it's the impedance of these two things in series. So this is not going to be R1, this will actually be Z1. And then again, we'll take our two limiting cases. So at high frequency, we're going to say that the impedance of the capacitor is negligible, right? So we said at high frequency. So remember that the impedance of a capacitor is 1 over j omega c, where j is the square root of minus 1. So then that gave us Z1 is R1 plus 1 over j omega c. So we'll say at high frequency, omega is very big, so the impedance of this capacitor is tiny. So we have Z1 is basically R1. And then at low frequency, so if omega goes to 0, then we have basically an infinite impedance, right? So we have Z1 goes to infinity. So then what that means is that in this case, so at high frequency, so this was V out over V in is 1 plus R2 over R1 at high frequency. And V out over V in is 1 at low frequency. Because, right, so at low frequency, so this Z1 is a big number, so you just get a big number in the denominator, means this second term is tiny, so you have V out is V in times 1 plus a tiny correction. And then at high frequency, instead, it's just V out is V in times 1 plus R2 over R1, right? And we got a microphone, we made a amplifier that could amplify the microphone signal by a factor of like 100, and meanwhile, it only multiplied by 1 the DC effects that were kind of annoying, like the op-amp imperfections. Okay, so that's just a reminder that in the past, we've put a resistor and a capacitor in series as kind of a sneaky trick to make the resistor appear gigantic at DC, or at very low frequency, but just to become equal to the resistor value at high frequency, at so-called signal frequencies. Okay, so we're using that same sneaky trick again. So let's look at what happens in this amplifier circuit at DC. So when there is no AC signal. So we said we were going to set R1 nominally to 500 ohms. So it's a potentiometer, can go between 0 and a kilo ohm, but we're just going to leave it nominally at 500 ohms, and then we can see later the effect of tweaking its value. So in that case, we're going to have the quiescent value of V base is this 9 volts. So we have VCC times R2 over R1 plus R2. So if R1 is a kilo ohm and R2 is 500 ohms, then this is 1/3 of 9 volts Right, so this is 9 volts times 1/3, so this is 3 volts. Okay, so in that case, our sort of nominal value, our quiescent value, here's a good vocabulary word. So quiescent, it's like when nothing is happening. So the quiescent. So the quiescent conditions are the conditions when there's sort of the DC quietness is there, there's no AC signal on top of it. So you have the DC conditions, and you have not yet perturbed the DC conditions with a time varying signal. We call that the quiescent state of our transistor amplifier. So we have 3 volts. So then if we always start out assuming the transistor is active until we derive a contradiction. So then we have the emitter voltage is just the base voltage minus our diode drop. So that's about 2.3 volts. And now for DC, so this impedance is infinite for DC. So we only need to look at RE1. So then we have the emitter current is, and then this is ground. So we don't need to subtract 2 voltages because the second voltage is 0. So we have, that's VE divided by RE1. So that would be 2.3 milliamps. And then, so usually when you're designing these circuits, you typically want to design them so that the quiescent emitter current is kind of in the 1 to 2 milliamp range. It's kind of a nominal value. And then you also want to look closely at what the quiescent collector voltage is, because so the ratio RC over RE, although in this case what we're doing with RE is a little complicated, but the choice of collector resistor will depend on your desired gain. But somehow you want to combine the choice of collector resistor with the quiescent collector current, which is about the same as the quiescent emitter current, so that the quiescent voltage at the collector is about halfway between the 2 power supply extremes. In this case, it's 0 and 9 volts. So we probably want the quiescent collector voltage to be somewhere around 4.5 volts. Yeah, and I think we even are arranging for that to happen, so that's pretty good. Actually, no, not quite. Yeah, so actually a better choice probably would have been to put the quiescent V collector at a little closer to 4.5 volts. It seems like this amplifier design didn't do that. Normally that is something you want to do, but just you won't often be designing your own transistor amplifiers, but normally you want the output to be able to swing up and down by as far as possible. So for a 2.3 milliamp quiescent current, see if this is 1K, you'd probably make this resistor a little bigger actually. You'd probably make it more like 2K so that you have the quiescent collector voltage more like 4.5 volts. But we'll just go with what we have written down here. So then you know that the quiescent collector current is approximately the same as the quiescent emitter current because the base current is tiny if we're not saturated. So then, fine. And then we have the quiescent collector voltage is this power supply voltage VC, and then we have the collector current times this collector resistance. So in this case, we have 9 volts minus 2.3 milliamps times 1 kilo ohm. So 9 minus 2.3 is like 6.7 volts. Yeah, so I think if you were really going to use this in real life, you would probably design it so that the quiescent collector voltage is more like 4.5 volts. So you could do that either by making the quiescent current bigger or by making that collector resistor bigger. But, okay, you've heard me say that about 3 times now. So it seems like this is hovering around 3 volts, and then the collector voltage should be hovering like around 6.5 volts, I guess. So then this was like 6.7 volts. And then what happens when we apply a delta at the base? So we have a time varying signal at the base. Okay, so now we have to account for the fact that this impedance is not infinite for an AC signal. So in fact, the effective, all right, so here, let me just go back. So we'll write down, remember on the previous board, we said that delta V collector per delta V base was minus RC over RE. But now we've done something tricky with RE because we effectively have, in this case, RE is RE1 in parallel with RE2 plus 1 over J omega C2. Okay. And we'll just, I won't work out the numbers here. You can work out the numbers that show that this 1 over J omega C2 term becomes negligible once you're at like a reasonable frequency, like let's say a kilohertz. So then this basically is that our effective emitter resistance for AC is RE1 parallel RE2. And remember, see, if you have 1,000 parallel 100, it's 100 minus about 10%, so it should be about 90, I think it's 91 ohms. So I think that's 91 ohms. All right. So, so that means we expect this to be like about minus 9. Yeah. Okay. So if this goes up by a delta V, then this goes down by about 9 delta V. So here, I'm trying to make, I'll exaggerate this a little bit. Yeah, so then like that. I'm not very good at drawing these things, but yeah. Okay. So if this is delta V, then this is like minus 9 delta V. Good. I think that might be all we need to do before we can try it. Yeah, so now we'll build the circuit and we'll give it a try. Okay, so here's how I built the circuit on the EE board. So I made waveform channel 1 come in over here on the left. And then this big capacitor is C1. And it's kind of hard to work with these 10 microfarad capacitors, so you kind of have to design everything else around where you put them, it seems. And I made oscilloscope channel 1 monitor the input signal, which is on the left side of C1. And then, let's see, last time I had a little trouble with this 10 microfarad capacitor spanning my kind of power supply wires here, so I just left the right-hand side of that capacitor over here. So I have this little blue wire to jump over from the right-hand side of C1 to where I'm making all my base connections. So here is where I'm making all my base connections in this column right here. Remember, my convention is I always use this red stripe on the top for plus 9 volts. And I always use this blue stripe on the bottom for ground. And we're not using it here, but I normally use this red stripe on the bottom for minus 9 volts. Oh, and then I'm going to use the phrase VCC to mean plus 9 volts. Now, somewhat confusingly, your Electronics Explorer board has a separate output that it calls VCC, which must be either 5 volts or 3.3 volts. Sorry about that. So what it calls VCC is different. So like in transistor circuits, normally you call the highest available voltage VCC and the lowest available voltage VEE. So don't let that confuse you, because we're not using what the EE board calls VCC here. We're using VP plus is 9 volts, and that's basically the only power supply we're using, and we're using ground. So I have my 1K resistor R1 here going from plus 9 volts to the place where I'm making all my base connections. And then I have my input signal from the right-hand side of C1 coming into where I'm making all my base connections. And then this is a 1K potentiometer. And I wired it up. This time I did something a little different from what I did last time. So this time, here's my 1K potentiometer. And this time I connected this end to ground, and I'm connecting this end up to the base. And this end is not connected to anything. Okay, so now as I turn the knob right and left, it will adjust the resistance. Actually, it's interesting. I guess I must have it pushed in upside down, because so I did connect it in a way that when I turn the knob to the right, the resistance increases, and when I turn the knob to the left, in other words, when I turn the knob clockwise, resistance increases. When I turn the knob counterclockwise, resistance decreases. And I guess I must have pushed the potentiometer in upside down. So anyway, fine. So you're going to see me turn the screwdriver to the right later to increase R2, and I'll turn it to the left to decrease R2. But this is how I connected it. So the middle, the wiper goes to the base, and then I connected to this little black wire goes from the right-hand side of the potentiometer down to ground. All right. What else do we have here? So now remember these 2N3904 or later 3906 transistors, the naming convention is EBC. Transistors are as easy as EBC. So emitter, then base, then collector. When you're looking at the flat side, the emitter, then the base, then the collector. So that's not always the most convenient for wiring things up if you want your circuit to look like your schematic diagram. Anyway, so EBC. So since the emitter is on the left, I want to put my emitter connections kind of on the right so it looks like my schematic diagram. So I use this little blue wire to jump the emitter over to this column so I can put my emitter connections over to the right. And then the base is in the middle, so I have this blue wire going from where I made all my base connections on the left into the base, because again, I want my circuit to look like my circuit diagram, so all my base connections are on the left and all my emitter connections are on the right. And then here's the collector. So I have this 1K resistor from the collector up to plus 9 volts. So there's my collector resistor. And then from the place where I'm making my emitter connections, I have this 1K resistor going to ground. And then I have this 100 ohm resistor. Again, this 10 microfarad capacitor is so big that you kind of have to work around it. So I have this 100 ohm resistor going to the top of that capacitor, and then the capacitor comes down here, and from the bottom of that capacitor I'm going down to ground. Okay, so that looks like this. So there's C2 and there's RE2, and here was RE1 over here. And then I have scope channel. It's actually really nice to have 4 scope channels for these transistor circuits. So I have scope channel 1 looking at the input signal on the left side of C1. I have scope channel 2 looking at the base. I have scope channel 3, and these are all DC coupled. I have scope channel 3 looking at the emitter, and then I have scope channel 4 looking at the collector, which is the output of this circuit, right? So the common emitter amplifier, its output is at the collector. Remember, the emitter follower's output was taken at the emitter. The common emitter amplifier's output is taken at the collector. And in both of those cases, the input is at the base. Okay, so then we can see, let's look and see what we got. I'll turn on the waveforms display. So let's compare what we read out with what we worked out on the board. So I haven't turned on the input signal yet, so it's just sitting at ground. So the yellow curve, channel 1, is just looking at V signal here, or V source. So it's just hovering around 0 volts. And then blue is channel 2. Blue, or cyan, is channel 2. So it's looking at the base. So it is pretty close to 3 volts. It looks like it says 3.01 volts. Okay, so I adjusted this. I turned the screw looking at the ohm meter until this R2 value was as close as I could get it to 500 ohms. So it seems like our base current really is quite negligible here. And then, and we could also estimate what we expect the effect of the base current to be. We could do that in a second. Okay, and then here's, R1 is okay. Right, so we expected this to be 3 volts because it's 9 volts times 500 over 1500. So 1/3 of 9 volts is 3 volts. Then we expect the emitter to be a diode drop below the base, so about 2.3 volts. So what we see is indeed 2.3 volts. That's pretty good. Okay, so that's the magenta trace, 2.3 volts. So you can see, maybe you can't quite read it, but I can read. This is like tens of millivolts with the minus sign, it turns out. This is 3.01 volts. This is 2.31 volts. And it fluctuates a little bit. And this is 6.71 volts. Okay, and then channel 4 of the scope, the green trace, is at the collector. So we predicted, we predicted this before I built it, huh? So we predicted 6.7 volts, and indeed we see 6.7 volts. That's cool. I can make this a little bigger so you can see the numbers, I guess. Okay, so you see the input signal is just floating around 0. It's measured in millivolts. The base, the cyan channel, channel 2, 3.0 volts. The emitter, the magenta channel, channel 3, 2.3 volts. The collector, the green channel, channel 4, 6.7 volts. So that's what we expected. And then, okay, so that's pretty good. So our calculations worked out. And then we think that if we put some kind of a time varying signal at the input, that we will see that the output varies with about -9 times, 9 times the amplitude and 180 degrees out of phase. So let's give that a try. So we'll go over to Mr. WaveGen here, and we wanted 10 kilohertz. Okay, so 10 kilohertz. 10 kilohertz, and an amplitude of 50 millivolts. Okay, so then we'll say go, and we'll look back here. Okay, so there's that signal, and there's that signal, and so 50 millivolts amplitude should be 100 millivolts peak to peak. So then times 9 should be 900 millivolts peak to peak. That's plausibly what we see here. So we'll zoom in a minute to look more closely. Yeah. Okay, let's look a little more closely to see if we can verify what the gain of this circuit is. So, how are we going to do that? We can, so it seems like this, we could AC couple, or we could, let's subtract. So let's, yeah, let's just subtract the average value of each one of these things. So I made all these things so that they nicely go between 0, well, I guess between -1 and +9 volts, so we can see them all together. That's kind of convenient, but let's take a closer look. Let's zoom in on channel 4 here. So instead of an offset of -4 volts, let's do an offset of -6.7 volts. Okay, and then for channel 1, I guess let's do an offset of 0 for channel 1. Okay, and then let's temporarily get channels 2 and 3 out of our way. And then let's go to, so on channel 1, let's go to like 100 millivolts per division. And on channel 4, let's go to 100 millivolts per division. That might be too fine a scale. And then, okay, this was 1 millisecond per division. Let's go to 100 microseconds per division. Okay, we can even go to like 50 microseconds per division. Now, I don't fully understand the fuzz. You sometimes do get fuzz with transistor circuits, and actually there are interesting tricks for dealing with this, like putting capacitors in between your power supplies. So this is a topic we probably ought to add to this course. Here, let's go to 200 millivolts per division. And okay, that's not bad. And then we'll put this at 200 millivolts per division. Yeah, so it's kind of bothersome that we have all this fuzz on the input signal we're looking at. Oh. Sometimes you could make the fuzz go away. Gee. By reducing like the loop area for stray radio frequency signals to come in. So like the loop area for things to couple magnetically to your signal. Anyway, okay, I guess for the moment I won't worry. Well, it's kind of annoying. I wonder if we could do average. Sometimes you can average, and that's one easy way to get. I haven't figured out how to do averaging on this thing though. Okay, well, let me let's just measure the amplitude of the outputs. You know, the amplitude of the input signal should be 100 millivolts peak to peak. So let's look at the amplitude of the output signal. And we're going to look channel 4 here, and we'll just trigger it once and stop. And seems like here we're going, this is like 7.22 volts. And I guess I'll just go in the middle here. And this is like 6.18 volts. 7.22 volts minus 6.18 volts. That seems like about 1 volt. So that would kind of correspond to roughly a gain of 10. I am kind of annoyed by the fuzz. I wonder if we can fix that. Let me see if I can fix that. Well, by wiggling the wires a little bit, I did get rid of the fuzz on the input signal. I did not succeed at getting rid of the fuzz on the output signal. But then I also added measurement values. So I used the measure function. So channel 1 amplitude, 43 millivolts roughly. Channel 4 amplitude, 430 millivolts roughly. So we have a gain of about 10. And you can see that when the input goes down, the output goes up. So there is 180 degrees phase difference between them. So that's pretty good. I guess, you can do a kind of a better quantitative measurement with Circuit Lab. I guess we could make the input signal a little bigger, and then that should make the effect of the fuzz be smaller. So let's try making our input signal be, well, here, let's just double it to 100 millivolts. So that's a little easier to see. And so then input amplitude roughly 90 millivolts, output amplitude roughly 0.9 volts. Then I guess we could go to 500 millivolts per division. And I'm pushing down on one of the wires to try to limit the fuzz. So this whole business of tracking down fuzz is kind of an interesting topic. The fuzz is sometimes called parasitic oscillation, and it happens often in amplifier circuits, especially at high frequencies. We can try to make this a little bigger. Let's try 200 millivolts. Yeah, the fuzz. Fuzz is annoying. Sometimes you can make it go away. Usually if you try hard enough, you can make it go away. Okay, then let's try even a little bigger. Wait, we're looking at channel 4 here. We really can't make it much bigger because we're getting up pretty close to 9 volts. Okay, so there are two things I want to do now. One is I want to show you what happens when, so it can kind of stop working because the transistor cuts off, or it can stop working because the transistor saturates. So typically you get a limit on the high side and on the low side when that happens. Let me first go through, let me just take a look at the instructions and see what else we were supposed to look at. Okay, so one instruction that I had skipped was adjust the potentiometer so the DC voltage at the base is about 2.25 volts. I instead just set it to 500 ohms. So let me do that now. And I miraculously fixed my fuzz problem by making the wire that I'm using for scope channel 1 shorter. So I just picked up the shortest wire that would make the desired connection for scope channel 1. And miraculously the fuzz is gone. So sometimes a long wire, especially a long wire that encloses a big loop area, then you can get a time-varying magnetic flux that induces an EMF in that wire, and you can magnetically pick up a signal that couples into your circuit and parasitically oscillates. Okay, I moved all 4 scope channels back to offset -4 volts and range 1 volt per division so that we can compare them all directly. So now we have 0 volts down here and 9 volts up here for every channel. So 0 volts is just 1 tick above the bottom. Let me now go and, here, I'll unplug the input signal, so then we're just reading a DC voltage. And then I can adjust the little screwdriver. Here, I'll let you see me adjusting the little screwdriver. So I will adjust the little screwdriver. until, what are we asked for? Until we get about 2.25 volts here, okay, at the base. Okay, so now we have 2.25 volts at the base. And then here, so we can go through and trace out what we see. So we said, okay, we have V base DC conditions. This is like 2.25, 2.25 volts. Oh, all right, all right. So we have V base DC conditions. V base is 2.25 volts. And so then we expect the emitter to be a diode drop below that. So it should be, well, 0.7, so it should be 1.55 volts roughly. What do we see? Oh, we see 1.53 volts. That's pretty good. Okay. And then I guess then we expect the emitter current to be 1.55 milliamps. And then the collector current should basically be the same. And then we expect the collector voltage to be 9 volts minus 1.55 volts, since it's VCC minus ICRC. So that should be 8.45 volts. No, 7.45 volts. 7.45 volts. So let's see if we get 7.45 volts there. And yeah, look at that, 7.46. Cool. Then we want to figure out what the base current ought to be. So the base current should be, for an active transistor, there's the collector current divided by beta. Actually, so it's convenient. I mean, so we actually expect beta to be about 150 for this transistor. So if we say beta is 155, then we expect the base current to be 10 microamps. And then, actually now we no longer know what R2 is, but I guess well, yeah, we don't really know what R2 is. So R1 parallel R2 should be pretty close to R2 because R2 is smaller. And what do? We put the base at 2.25 volts. Let me just estimate what that is. So I worked out that in order for V base to be 2.25 volts, we must have set R2 to be about 333 ohms. And then R1 parallel R2 is about 250 ohms. And then you multiply that by this base current of 10 microamps estimated. And you would estimate that the effect on V base of that I base is about 2.5 millivolts. Because remember, V base is 9 volts times R2 over R2 plus R1, and then minus I base times R2 parallel R1. So this is what you get if there's no base current, just the voltage divider equation, and then this is the effect of the non-zero base current. It's the I base, and then the Thevenin resistance is the parallel combination of R1 and R2. Okay, so I think that the effect of the base current, because these resistors are so small, the effect of the base current is going to be too small for us to see. What else do we want to look at? Well, just for fun, I replaced the little jumper wire that, well, basically I measured the base current. I made the base current run through my microammeter here, and I measured 9.1 microamps. So that's pretty close to our estimate of 10 microamps. So it seems like beta is a little bigger than the 155 value that we just kind of assumed. And the way I arranged for that to happen is I just I took out the little wire that was carrying the base current and I replaced it basically with the multimeter. So I guess that gives us a measured beta of 170 because 1.55 milliamps divided by 9.1 microamps is 170. All right. Okay, I think we finished doing everything that the write-up asked us to do. So now I want to play a little bit. So here are the waveforms. So I had temporarily disconnected the AWG input. Let me reconnect that. Okay. Actually, one thing you notice is that if you look closely, the shape of this green sine wave is a little bit distorted. So you see it's flattened out a little on the top, and it's kind of sharpened up a little on the bottom. And that's basically an effect of this sort of nonlinear IV curve shape, the kind of diode-like IV curve for the base emitter junction. So I think we may talk about that a little bit later. Then I think I want to try to turn up the amplitude and see this thing fail. So what happens when the collector gets too close to 9 volts is that the emitter should be getting too close to 0. So we should be basically cutting off. I think that's a little, yeah. Okay, let's turn up the amplitude on the input signal a little more and see what happens. So here's wave gen. So we were at 200 millivolts. Let's go to 500 millivolts. Oh, no, we don't, gosh, we don't want 5 volts. We want half a volt. There we go. 500 millivolts. Okay, and we'll go back over here. Yeah, so you see this really is flattened out. And then, okay, so one thing you can see is that VBE becomes too small to keep the transistor active over here. So you can see that the base is only about 0.2 of a volt above the emitter here, so VBE has become too small. It's a little confusing that the emitter doesn't go all the way down to 0 when that happens. And I think we're being a little bit confused by this big 10 microfarad capacitor. I think this is the same confusing thing that we saw with the emitter follower. We were trying to figure out what happens when the transistor cuts off, and it was a little bit hard to understand exactly what the lower range is when the transistor cuts off. I guess if we removed C2, then we would have a sort of an easier situation to analyze. Anyway, maybe we won't do that. We could do that in Circuit Lab if we wanted to. Instead, just notice that the transistor does cut off down there. So the collector current is 0. That kind of makes sense because VCC minus RCIC is just VCC. So when we have this flat spot up here at 9 volts, the collector current is 0, and that corresponds to the transistor being cut off, which corresponds to the base emitter voltage being really small, smaller than a diode drop. And then I guess that's all we notice. We could think if we increase the amplitude even a little more, we could see this thing saturate. You could see it. You could see that the bottom part of the waveform is affected by saturation. So I guess we could try to make the input waveform even a little bigger. Like how about a whole volt amplitude? Oh yeah. Okay. So now you see And then let's change the time base so that we can, oh, where is the time scale? Oh, that's kind of weird. Okay, so okay, so then you can see that there's this flat spot on the bottom now. Oh, where are we? There's this flat spot on the bottom now. And so when that happens, we see that the collector has gone below the base. So that's transistor saturation. And then you can see, yeah, so now during saturation, the collector is somewhere in between the emitter voltage and the base voltage. So basically, VCB has gone negative. And if we looked closely, we would see that now there is significant base current. So in saturation, you no longer have this nice factor of beta between the collector current and the base current. And you no longer have negligible base current. And then wiggling the base no longer directly affects the collector so easily. So basically, the collector current is sort of as on as it can be. So you can see now the top of our waveform where we don't have linear amplification because the transistor is cut off. And the bottom of our waveform, I mean the collector waveform, the bottom of the collector waveform, we don't have nice linear amplification because the transistor is saturated. And so it's sort of interesting to explore those two limiting cases. All right, I think that's all we'll do on the common emitter amplifier with the EE board.